from our Teams page. Yes. Yeah, people are writing stuff. Okay, so everybody is muting their microphones. In case you like to talk, then you can talk. Okay, let's start. So yesterday we talked about this. Let me see if my pen is working. Yeah, you see it, right? Yeah, yesterday we talked about this, and we said that now we are using how many? Now we are using. Let me try to see if I can take this out. How can I make this? Okay, I couldn't make it go away. Okay, so we have these producer and consumer, these two threads. This is for mutual exclusion, again mutual exclusion, and this is for again releasing the lock, and this is for counting the. Sorry. This is for mutual exclusion, and this is for mutual exclusion, and these are removing the locks, right? And then what we have is we have total of 1, 2, 3 semaphores. This is for mutual exclusion critical section. These are for counting the empty slots and etc. Okay, good. So question: what happens if I do this? If I replace these two positions, and if I replace these. Okay, you understand what I mean, right? I replace those. What happens? Would this still work? Consumer, producer, consumer with semaphores. Will it still work? Anybody? Are you there? What happened? Okay, let me go back to meeting, join. Does anybody has the answer? Can you hear me? It looks like I am talking to myself. Where is my Teams? Okay, go back. Okay, Furkan said something. Furkan says the critical region will change. Yes, it says, I think it will be locked, and people say, I think it will be locked. Yes, somebody says yes, because full is initially 0, the critical region will change. The thing is this, my pen is out. I don't know what happened. Okay, maybe I can use the mouse cursor. Okay, I am changing these two, and I am changing these two. Let me go get my regular mouse. Okay, so the thing is, can somebody talk?
Yes, I can hear you, teacher.
I lost my connection. Something has crashed. I don't know what's going on. Bad network quality. Again. This is my conversation. Okay. Conversation. Okay, good. Okay. The thing is, that would be a bad thing, because if I replace the positions of these two, okay, if I replace the positions of these two, that means that I am locking I am getting the lock for the critical region first, and I do an empty down on empty. If I get blocked on this empty, that means that I hold the lock, right? I hold the lock, and I cannot continue because I am waiting on empty, because empty is 0, okay? So that means that I hold the lock when I am waiting for something. Who is going to make this empty non-zero? This one is going to do it, but this one cannot enter the critical region because I am holding the lock. Okay, so that's not a good thing. That's not a good thing. If that happens, if I replace those two, the positions of those two, this code will not work. From time to time, it will get into an infinite deadlock. Okay, so that's not a good thing. Okay, you understand? Somebody say something. Can you talk? Somebody
Yes,
talk.
we understand.
Okay, I think it was Mustafa, right? Mustafa, is that you?
Yeah, yes, teacher.
Mustafa, for some reason only you can talk. Okay, sir, can you explain again? The thing is this. If I put mutex in front of empty, right? Okay, I run mutex, down mutex, I got the lock, and I am trying to, remember I do this before, okay? Okay, so this is down mutex, and I don't have this. I get the mutex, okay, I hold the lock, and I'm trying to decrement empty. Let's say the value of empty is 0. If it is 0, I will get blocked, right? I cannot continue. So this thread is blocked. It is waiting so that empty should be greater than 1. Who is going to make empty greater than 1? This one, right? Up empty. But this one cannot continue because this one cannot get the lock. Lock is held by me, and I am waiting for the mutex, right? And I am waiting for the empty, and empty cannot be upped. So that's what's wrong with this. Okay, Kamil, do you understand now? Kamil, say something. Kamil, just talk. Say yes. Say yes with your voice.
Yes.
Yes.
Okay, good. Kamil can talk. Doğancan, but would it work if we remove the mutex from both sides? It looks like it would. Well, if you remove mutex, okay, then that means that you don't have the critical region anymore. Okay, if you insert an item, and if the other part is, see, if you that's a very good question, Doğancan. Doğancan, you are asking good questions. Okay, that means that this online thing is working for you. Okay. So Doğancan says that let's okay, I think I asked this question yesterday. You are saying this, right? You are saying this, Doğancan, right? Doğancan, just talk. Say yes. Do you mean this? Is my connection? Doğancan, are you there? So still we have a delay, right? So if I remove these mutexes, that means that I don't have the critical region anymore, right? So while I am inserting something, I could be removing something too. So that would be a race condition. So I cannot remove this mutex, mutual exclusion. This is for mutual exclusion. These are for counting the empty and full slots of the buffer, okay? And note that empty plus full is always n. Okay, it is always n. Okay, so that's good. So this is a very nice piece of code, and it tells you how to use semaphores to implement producer-consumer problem. Again, producer-consumer problem is not a toy problem. Many inter-process communication applications can be modeled as a producer-consumer problem. Okay, if there are no questions, then I can move on. Any questions? Okay, no, good. Okay, so actually we use two types of semaphores. One is the counting semaphores that has empty and V down empty, V down empty, V down full, V up empty, and V up full. So these are for counting semaphores. I do n 100 times down, and the 100th down is a block. I know that, right? Okay. So similarly for the down for the full. So it is these are for counting semaphores. Counting semaphores are not for critical regions. Okay. They are trying to see if a condition holds. Okay. I am trying to say that critical regions are important, but I know that I need this many buffers and etc. Okay, so they are good for synchronization, used for sleep wake up when the buffer is in the something weird is happening. My internet connection goes away and comes back. No, but I will find a solution. Okay, so I use the counting semaphores for synchronization, but my other type of semaphore is the mutual exclusion semaphore. They could be only 1 or 0. Okay, I use it to protect access to a buffer. Okay, good. So I use semaphores for these two cases, and some people say that maybe these are very special. Maybe we should not call them as semaphores. We will call them mutexes. Okay, mutual exclusion stuff. Okay. If you have any questions, good. So mutexes are this special case of. It says bad network quality. Do you still see my? Do you still see my screen?
Yes, I can see, but your voice interrupted often.
It is often. It is bad.
Yeah.
You don't understand what I am saying? Okay, let me try to do this then. Let me switch to some other connection type. Okay, and this and that. How about this? Can you see me and can you hear me?
Yeah, I can hear.
How about other people? They are okay?
Nobody
Okay.
talks.
So everybody, okay. This is better. Okay. So these mutexes are special case of semaphores. Special case of semaphores. They are only for 0 and 1 only. 0 and 1 only. Okay. They are only for 0 and 1. And use critical regions. Try to grab a lock. If unsuccessful, let another thread run. If fail to acquire a lock, then yield. Again, I'm saying the same thing. I don't understand what's going on. Am I being interrupted again? Am I being interrupted?
Yeah, yes.
I don't know what's going on. Okay, I will continue if I don't have any questions. So mutexes are this. Mutexes are can be implemented using our TSL instructions. Okay, our TSL instructions are. Let me try to. I cannot see your questions if I don't do that. Like, let me see if I. No, I can't. Anyway, I will try to solve this during the break. Mutexes can be implemented using our TSL instructions. This is a typical mutex. It says that load this mutex value to register and compare it against 0, and then if it is 0, then return from the mutex. Otherwise, you see this. It says thread yield. So this is not busy waiting, right? This is not busy waiting. Okay, this is not busy waiting. This is just calling the thread yield. So the operating system or the thread library just can make somebody else work. If I return from this thread yield, I just jump back to the mutex lock and do the same thing again. So I am not in a busy loop, spin lock, but it's kind of a spin lock, but it's not a busy loop. It uses the sleep, and for the unlock, it is as simple as putting a 0 to the mutex. Okay, any questions? Okay, let me see if I. Okay, Barish has a question. He says, "Is the main difference between mutex and mutex and binary semaphore?" No, but there is no difference between a mutex and binary semaphore. Binary semaphores are mutexes. Okay. Yes, TSL is a atomic instruction. We talked about this yesterday. That's true. Okay. Good. Go back to the slide again. Let me put this in this corner. Okay, so mutexes can be implemented this way. Actually, you could implement semaphores using the TSL instruction. That's more involved, but I am not going to talk about it. So so far we looked at the threads, inter-process communication between the threads. They share the same address space. So once they reach to the once they modify the global variables, then I am okay, no problem. What happens if I try to communicate between the processes which do not have any common spaces between themselves, what happens if I do that? If I do that, then I need to use some space in the kernel, or I need to use some mechanisms from the operating systems. Okay, operating systems tells me that this space is a shared space and I can use it. One example is the shared files. Remember the files? Just the files. If two processes, process number one and process number two, opens the same file on the desk, okay, they can both read and write. That means that they have a common space, right, to read and write. But you might say that file is on a desk and it would be too slow. Yeah, that's true. But the operating system can open the file in the memory. There are some memory mapped files. Memory mapped files. If you use memory mapped files, the file is actually on your memory, and reaching your file is very, very fast. Modifying your file is very, very fast. This is how you can deal with the communicating between two processes. Okay, good. Another concept is, any questions? Okay. This thing is killing me. Something is, let me, if I take this out, I think I will take this out. Okay, good. The other thing is, see, this is not busy waiting, okay? This is not busy waiting, and we said that busy waiting is expensive. It keeps the CPU busy, but this call is expensive too, okay? Because if you are using operating system level threads, then thread yield means the context switch. Context switch is a bad thing, okay? So which one is actually more expensive? Which one is cheaper? They thought about this and they invented this fast user space Mutex, okay? It says that block only if necessary and switch to the kernel space, okay? So what you do is you ask the mutex to be locked. If the mutex is available, then you get it. Otherwise, you don't get locked. You do something else. Okay, you are in a wait queue. Okay, and after a while, you may need to go to sleep. But if that lock happens to be available in a few cycles, then you will get it and you will continue. Okay. So the fast user space mutex is kind of a hybrid approach between the busy waiting and the sleep and wake up system. Okay. So there is more detail in the book. I'm not going to talk about it much. Okay, any questions? We will talk about the memory mapped files in the I/O section. I/O section of the book, or I/O chapter of the book, okay? So the operating system says that this part of the memory will be treated like a file, and any process can open that file, write to it, or read from it. So that means that you have a common space. No problem. Another question from Ihsan. Is cold thread yield the only difference between mutex and semaphore? No, of course not. Mutex is binary. It is only 0 or 1. Okay, 0 or 1. Semaphore is a counting thing. It just counts from 0 to up to an n. Okay, so semaphore is much more complicated than mutex. Semaphore is not a busy waiting mechanism. Okay, semaphore uses sleep and wake up too. Okay, if you down a semaphore, which is a 0, value 0, then it goes to sleep until that value is incremented by somebody else. Okay, semaphore is for counting. Mutexes are counting, but since they can be only 0 or 1, they are kind of binary semaphores. Okay, so let me put it in there. Semaphores, mutexes are binary semaphores. Okay, so mutexes are specialized versions of the semaphores. Remember this example, always remember this example. Mutex, this could be only 0 or 1, but this empty could be from 0 to up to n. This full could be 0 up to n. Okay, good. Okay, let me go back then. Oh, okay, I can do this. Good. So fast user space mutex is something between, which one is faster, we don't know. I mean, busy wait or block. It depends on the case. If the wait is going to be short, then it is much faster instead of making a system call. But it's going to be long, many cycles, then maybe it is better to block. Okay, so how do we support threads with the pthreads library? Pthreads library, something happened. Something happened. I don't know what happened. Let me see. Okay, Yusuf İnce, Yusuf, you made it. And Yusuf made it, and now we are how many people? We have 66 people.
Tamam. Biraz sürebilirim acil. Seninle ben arada geleyim şey.
Yok konu şey yani. Bunu açacağız gibi gözüküyor da bilgin olsun. Ben devam soracağım.
Okay, let me. Who is YI? Yusuf İnce. Okay, Yusuf, keep your microphone muted.
Tamam
Okay.
hocam.
Good. So let's go back. So we support these mutexes with the thread library. Thread library has for the mutex initialization and destruction. These two things are simple enough. I can get that mutex lock or unlock. And how about this? Try lock. That's a very nice function actually. You try to get the lock. Okay, you try to get the lock. If you get it, okay, you are fine, you get the lock. If you don't get it, you don't get blocked. Okay, you get back your control and you do something else instead of getting blocked. Maybe try again, maybe try 50 times. After the 50th try, if you still get the if you still don't get the lock, maybe you should just call lock and block. Okay, so this will never block. This will block if the lock is not available. Okay, so those are the differences. So let's see some examples using the mutexes. Remember, we use the mutexes like this. We said that this is a mutex, this is a mutex. These are counting semaphores. And I like to write this producer-consumer problem using the pthreads library mutexes. So I need some way of doing the counting, okay? Instead of using the regular semaphores, pthreads library offers something else. It says that I will let you use these. I don't know what to do with the stupid. Can I? Oh, okay, I can minimize it. It says that I will offer you these condition variables. Condition variables are more useful, easy to use than semaphores, and they are supposed to be used with the mutexes. So the condition variables and mutexes they are almost always used together. Okay. These are for critical regions. These are for counting something, trying to see if a condition has happened or not. Okay. These are more general than the semaphores. Mutexes are good for allowing blocking access to critical region. Condition variables allow threads to block due to some condition. And that some condition depends on depends on your program logic, okay? So remember our semaphores, they can block, but they are only for counting, right? What if I need more than counting? What if I need to do something else? Okay, so let's try to implement this producer-consumer problem using the condition variables and the mutexes. So these are some functions from the pthreads library again. Condition init destroy, wait and signal and broadcast. Wait means that I am waiting for some condition to happen. So this one will block if that condition is not satisfied. I am waiting for some condition to happen. Signal means that a condition has happened. Wake up, anybody waiting for it. Broadcast means that, okay. Signal whoever is waiting for this to happen. Wake up everybody, okay. So signal wakes up a single thread. Broadcast, wake up, broadcast wakes up everybody who are waiting, okay. So these are the 5 basic functions regarding the condition variables. So we are going to use these. Also, we are going to use these 5 to make a producer-consumer implementation. Okay, let me see if I have any questions. Why mutexes are implemented within threads? Because without the threads, mutex doesn't mean much. Gebze, is that your question? Without the threads, mutex doesn't make any sense. You understand? In the thread library, that's the reason. Without the threads, mutexes doesn't mean anything, so it has to be with the thread library. I think you will understand it better when I make this. I think you will understand it better when I make this when I show you this new program. Can't we use mutexes in processes? No, you cannot. Well, you cannot use mutexes for the critical region between 2 processes. Why? Because processes don't share address spaces. They don't share address spaces. Okay. To share address spaces between 2 processes, you need some specialized solutions like the sharing of a memory mapped file. Okay. It is not impossible to implement mutexes outside of threads. Yes. If you like to use mutexes with the memory mapped files, you could do that, but they are often used together, so they made if you are writing a threads library, maybe you should offer these kind of nice synchronization tools like the mutexes and the condition variables. Okay. Good. So this is the threads library.
I cannot hear it, sir.
Mikrofonunuz kapalı.
Your sound is gone.
I don't know how I did it, but I think I turned off my sound, my mic. So you did not hear me when? Starting when? I mean, you did not hear me for the last 5 minutes, 10 minutes? How long?
1 minute.
4 minutes? So when I answer this question, did you get the answer to this question? 1 minute? Did you get the answer for this question?
We get the answer for that question. It was gone for 1 or 2 minutes.
Okay, so let's go back then. After that, I didn't do much. Let's go back to this program. And I said that we are going to implement producer-consumer problem using the producer-consumer problem using the threads library. Okay, so here at the beginning, I have this mutex, a single mutex, and these are my condition variables. Condition variable for the consumer and condition variable for the producer. My buffer is a single buffer, just a stupid integer buffer. My producer is very simple. Producer says that I will run a loop from 1 to max, which is a large number, and I will put this I to my buffer, okay? And the consumer says that I will get the buffer, the value at the buffer, and I will make it 0. So this is how you consume your buffer, okay? This is how you produce it, and this is how you consume it. Well, as you see, it is just stupid example, but it's a good consumer producer code, okay? So producer and consumer are two different threads. Let me show you the main function actually. Main function says that I have two threads, producer and consumer. Okay. And I am initializing my mutex. Remember my mutex and condition variables, they are all global variables. So I will initialize my mutex. I will initialize my condition variable for the consumer, condition variable for the producer, and I create two threads, sorry. I created two threads. One is the consumer and the other one is the producer. For the consumer, I have this function consumer. See, consumer function consumer and producer function producer. Okay, then after I created them, I wait until they end. I call this pthread join. Then I destroy my condition variables and I destroy my mutex. Okay, let's look at this implementation of the producer and consumer at the same time. Okay, do I have any questions? Let me see. Starting off library page. Okay, good. I don't know. Is it just me? But I don't know. I think there is a connection problem at the university. I don't know what's going on. I mean, we didn't have this problem yesterday with YouTube, right?
YouTube is very bad, very good.
It was better than this. Maybe switch to YouTube again.
Yes.
Yeah, exactly.
But with the YouTube, it was impossible to make a discussion between yourself. I mean, when I ask a question, it takes you like 60 seconds to give me an answer.
Yeah, so but there is very good.
Okay, so we can try Twitch. Twitch is not really. Well, Twitch is a better real time, right? Isan, Twitch is in terms of responsiveness, is it better than YouTube? Maybe we can try that too. Yeah. Okay, I will think about it. So let's go back to the example again. So I just write this I to buffer and I just erase it. That's what I do. Okay. So as you see at the beginning, I do this. This is my critical region. I like the mutex and I unlock the mutex. And inside my mutex, okay, inside my mutex, mutual exclusive region, I say that if the buffer is not 0, okay, there is a while loop. I call pthread condition wait and condition p and the mutex. Let's ignore this part for now, the mutex part. I say that if buffer is not 0, that means that nobody has read it. I cannot overwrite it, okay? I need buffer to be 0. If the buffer is not 0, I cannot rewrite to it. Buffer is full, it is not empty. So I am waiting for a condition variable to happen. I say that I am waiting this condition P to be signaled to me. If buffer, question? Okay. If buffer if buffer is 0, then I will say that, okay, I make my buffer I, and I signal this condition C, consumer condition. So since buffer is 0, I made it non-zero, then I can wake up the consumer. And I wake up the consumer and I unlock the mutex. Okay. And just the opposite, when I look at the consumer says that I will get the lock first. This is my critical region. I will get the lock first. If buffer is 0, that means that nobody has written to it. I need to wait for a condition variable. That condition variable is condition C, and that condition C will come from this point. See this condition C like that, and condition P is like that. Okay, so it says that I will wait for condition C to happen. Again, ignore this part. I will wait for it if the buffer is 0, and when I get the wake up call, then I will check this again. If the buffer is not 0, then I will read that value, okay, and I will make it 0, and I will condition the producer so that the producer can wake up and continue. Okay, so question for you. Remember what I said before when we looked at the code about the producer consumer problem? Like maybe, yeah, good, okay. It says that first down empty, then down mutex. So I said that if I replace these two lines, okay, if I replace these two lines, that would be a bad thing, right? But it looks like with this example, I just do that. I get the mutex first, and I am trying to wait for the condition variable to happen. I am doing exactly the same mistake. What I said before, it was a mistake. Now I am doing the mistake. So, well, this is not a mistake actually. This code works. Do you have an explanation for this? I think that wait function is taking and giving the mutex lock. Is taking and giving. Well, Doğancan, can you explain it a little bit? Wait function is taking and giving the mutex lock. Oh, you mean the taking is okay. You mean maybe this. You mean there's pthread condition wait takes the mutex lock as a parameter. This one says that if I wait for this condition to happen, since I am in a mutually exclusive region, critical region, this is the lock for the critical region. I will make this lock available so that this one can take the lock, right? So this one makes the mutex lock temporarily available for the other threads, So that's why this one and this one takes the mutex. I think this is what you meant, right, Doğancan? So this is exactly what I said about the previous program. I said that we should not do that, but there is a special case. You say that take the mutex and do this and etc. Putting the mutex at the beginning and at the end like this is better solution. Why? Because I get to play with the buffer inside this critical region. In the other one, I had to be careful because my critical region was much smaller than this. Okay, so the condition variables, as you see, this is a producer-consumer problem example again. It uses the condition variables. It doesn't use the semaphores. Okay, it doesn't use the counting semaphore. The condition depends on me. The condition is this: is the buffer empty? Okay, is the buffer available? So I make the condition myself. I don't count on the semaphore conditions. What are the semaphore conditions? It is counting down to 0. If it is 0, then I will block. That was the only thing that you can do. But with this one, the logic belongs to me. I can do anything. I can do anything I like. In this case, my condition is this. In other cases, it could be call some function with some parameters, and if it is returns true, then that's my condition, right? So conditions could be as complicated as I like for these condition variables. With the semaphores, the blocking condition is only, did I reach the number 0 or not? Okay. Okay, good. So these are the condition variables. So instead of using semaphores, we use this. Okay, any questions? Any questions? Okay, let me continue if there are no questions. As you see, it is not that easy to make this kind of programming. I mean, using the semaphores, mutexes, condition variables, and the thread library, and etc. Often when you write a parallel program like this, you make a mistake. And when you make a mistake, your program will crash or will go into a deadlock or will show you some kind of a race condition from time to time. The bad thing is that you get this kind of behavior not all the time, but intermittently. So that's a bad thing, bad type of programming error. So what are we going to do? They say that, okay, let's try to help the programmer. Okay, let's try to help the programmer by introducing some higher level constructs. Okay. What do I mean? Let's directly support these mutexes and the condition variables with the programming language itself. Okay, Java was one of the programming languages that did this. Okay, this new programming concept is monitors. Okay, people offered this in 1970s, and Java has these monitors. The original C++, they don't have it. With the new versions of the C++, we have it, but in the original C++, we don't have it. Okay, so monitor is like a class actually, but within that class, only one thread can be active anytime. Okay, so in other words, they are the language implementation of the mutexes. Okay, here's one example. This is a monitor. Okay, inside the monitor, I have a condition variable. I have producer and consumer. Okay, of course, you could call this producer or consumer of this class, but only one producer or only one consumer can run at the same time. if I am running the producer, nobody else can run the producer at the same time. So this mutual exclusion is automatically handled by the programming language. Okay, mutual exclusion is automatically handled by the programming language. So you don't need to worry about the mutexes. All you need to worry about is the condition variable. Okay, that's the idea of the monitors, and we are going to see an example in a few minutes if I don't have any questions. Okay, Barış has a question. In case of multiple thread producer consumer, which one is multiple thread? You mean more than two, Barış? We already, I mean, two is multiple. Okay. I have things. I can send praises. Doğancan, I was going to send you a praise. Let me send you a praise. How am I going to send you? Awesome. I am sending you an awesome praise now. Okay. How do I, what? Preview? Send. Did you get my praise, Doğancan? Oh, okay, everybody sees it. Whoever asks a question, I will send a praise. Okay, Barış. If you have more than two, let's go back. That's a very good question. Barış, I am going to send you another praise. Okay, how am I gonna send you a praise now? This, no, this, what is this? Reorganization video. It's so difficult to send a, okay. I am trying to motivate you. You don't understand? Select a badge. Which one do you like? Which one do you like? Kind heart? Which one do you like, Barış? Achiever. Unicorn. Well, I'm out of unicorns. Doğancan got it. Oh, your name is doesn't. Okay. Okay, I found it. Barış, I don't want to send my praise to some wrong person. Okay. So, two praises. Okay. So keep these somewhere. They will be useful. Okay, let me go back to the. Well, let's go back to the original producer consumer example. This one. But it says that can I use more than two threads to do this producer consumer thing? Let's say I have producer 1, producer 2, and producer 3, and I have one consumer. Does it work this way? The answer is yes, of course. Yeah, no problem. Why? Because every time I make, I run as a producer this loop, I down empty, okay, I get a new slot, and I enter the critical region, and I outside of critical region. So it doesn't make any distinction between who is making this down and who is making this up. This is different from Patterson's algorithm. Remember, in the Patterson's algorithm, I had this turn variable. Also, I have this interested array which has two parts, right? This one is interested, or I am interested. Okay, this one doesn't talk about that kind of constraint. No, I mean that's why we like these mutex solutions, condition variable solutions. They are easily generalizable to many processes at the same time. Okay, which is not the case with the Patterson's algorithm. Of course, Patterson's algorithm can be generalized to more than two threads at the same time, but you need to generalize them. Okay, and the generalization is not as easy as the two-thread case. Okay, good. Any other questions? Why the monitors isn't implemented for C and C++? That's a C++ decision. I mean, threads are not directly supported by C and C++, right? Thread library is outside of the C and C++. P-threads, they are just libraries. I mean, they are libraries like any library can be added to C and C++, that they are not part of the language. Okay. C and the logic of C say that language should be very, very simple. Okay. Don't talk about those kind of special cases. Just very simple language. Do the basics. The rest can be implemented using the libraries. Even the thread libraries, these kind of mutexes and semaphores and etc. Okay. Good. So since you asked a question, Shevki, I am going to send you another praise. Which one do you want? Creative. Problem solver. Okay. Good. So let's go back to our monitors again. And as I said before, this is just an example of a monitor, and this is some information about the monitors. Okay, mutual exclusion comes free with the monitors. Okay, because only one process or thread can be active in a monitor at any instant. Only one process. Only one process can be active in a monitor at an instant. So mutual exclusion is done automatically. With the condition variables along with the operations on them, wait and signal. If I am waiting for something to happen, I will wait for it. Signal will wake me up. Okay. So this will be very similar to what we did before, only I don't have to think about the mutexes. So let's see a Java example. This example is not a Java example, but let's see this example first, and then we are going to look at the Java example. But before that, maybe I should take some break, right? Any questions? Let's take some break, 10 minutes of break. It is 11:32 now. Let's come back together at 11:42. Does monitors supported for both threads and processes? Well, Gökçe, you will see that the example that I'm going to give you is about threads. Java directly doesn't support processes because processes are kind of operating system dependent. Threads are lightweight and they kind of behave similarly under Linux or Windows or other operating systems. Okay, so the monitors are actually for threads. At least the one that I'm going to show you are for threads. I mean, if you like to communicate between the processes, that's going to be more work. Okay, that's why they have invented these threads. With the threads, data sharing is more convenient. Okay, as long as you are careful about the race conditions. Also, it is much more efficient to switch between the threads. You get lots of help from the hardware. So Gökçe, for some reason you don't like threads. You always ask questions about how about processes. I mean, if it makes you feel good, I mean, we like processes too. As you know, without the processes, there are no threads, right? So rest assured that we like processes too. So 11:42, 10 minutes. I mean, it's going to help. I can send you a praise so that you feel better. How about this one? Thank you. Okay. Did this solve your process? Process problem. I think it should help. Okay, let's begin. Well, there was a question about C++ doesn't support it. Yeah, well, as I said, C++ is not concerned about those kind of details, but if you like, there are monitor, you can implement your monitor class using the mutexes. This std mutex is an addition for C++ 11. Okay, so the C++ 11 directly supports threading, multi-threading, and the mutex and etc. But they don't directly support monitors. But for monitors, the important thing is you could lock a mutex every time you make a function call within that class. That's what you do. Okay, so let's go back and look at this monitor. Do I have any questions? See if I have any questions. No questions. Okay, let's continue then. Here is our monitor. This is our monitor. Inside our monitor, I have two condition variables, and I have a buffer. Okay. Remember this insert and remove. Only one of them can be active, and if two different threads makes a call to these functions, only one of them will get true. The other one will have to wait. Okay, insert says that I will take an integer. Okay, if the count is n, that is, if the buffer is full, then I will wait for this full condition. Otherwise, I will insert the item and I will increment the count. If count is 1, that means that count used to be 0, now it is 1. That means that my buffer is not empty anymore. So I will signal the empty. The function remove is if it says that very similar, very parallel thing. If count is 0, that means that buffer is empty. So I cannot remove anything. So what do? I am going to wait until I get this empty condition signal. If count is not 0, then I will remove the item, decrement the count by 1. And in that case, if count becomes n minus 1, that means that the whole buffer used to be full. Okay, so there is a slot available now. I will signal full so that the producer can produce something. So this one corresponds to this one. Okay, signal goes to wait, and this signal goes to this wait there. So this is my complete producer consumer monitor class, and my client code becomes so simple. All I do is for the producer in an infinite loop, I produce an item and I insert it. For the consumer in a loop, I remove the item and I consumed it. So this part of the code is so simple. So it doesn't care about the inter-process communication, mutexes, and that kind of stuff. This one, as you see, doesn't care about the mutexes. All it cares about the conditions that is happening, the full and empty conditions. So I don't use the mutex. Okay. Java implemented threads user level, right? I think Java monitors works at user level. So how can? Well, I mean, it depends on the JVM. I mean, I cannot say that this threads library is implemented at the user level or the operating system level. I don't think that they document it. So they don't want to make that kind of a promise. Okay. Somebody has asked a question. So Ozan, the answer is we don't know actually. I don't know if Java implemented in the it depends on the operating system. It depends on the JVM virtual machine. Okay, so let's go back and check how the monitors are doing this with the Java programming language. So this one is our class producer consumer, And inside the producer consumer, I have a static class that is for a thread. This producer is a thread. Okay, producer is a thread because it extends this threads superclass. And run, you have to provide it, otherwise you don't become a thread. It says that I have an item, I produce an item, and I insert it in an infinite loop. So this one is very similar to this loop, right? Very similar. So produce item is something very stupid. I mean, just produce an integer and gives it to me. And there is a monitor, and our monitor is this one. So this one is going to be our monitor. Our monitor is a monitor class, and we're going to see it. Okay, so n is the buffer size, my producer and my consumer, new producer, new consumer. Okay, those are the two threads. In my main method, I call pstart and pstart, cstart. So they both start running at the beginning of the program. And producer does this. It just says in an infinite loop, I produce items and I will insert them to the monitor. Okay, so the consumer part is very similar to this one. It won't be that interesting. And this is the consumer part. Okay, so this run method, it says that I will remove an item and I will consume it. As you see, this one and this one doesn't care about the mutexes. They don't care about the inter-process communication. They are very regular code. It is very easy to write, easy to understand. The complicated part is with the monitor class. But again, even with the monitor class, since I don't have to deal with the mutual exclusion, that's relatively easier, the our monitor. So let's look at this, our monitor class. Our monitor class starts here. Static class. See, this one is the our main class. This is an inner class, another inner class, and this is our third inner class. Okay, static class, our monitor. Inside it, I have my private buffer of n integers. Okay, and I have my count and low index and high index. It looks like we are going to use a circular buffer, right? So the circular buffer is like, you remember from the data structures course, this is low, this is high, and this high could be sometimes pointing to the upper part, right? So these are our indexes, and this is our index method, insert method, and these are remove method. And see this keyword, this is a Java keyword. You say that this is a synchronized method. No two threads can be inside this method at the same time. This is synchronized. So synchronization, this kind of thread support or the monitor support is provided by the core Java language. So synchronized is a keyword used by Java, and you say that no two methods. See this our monitor class. I didn't say that this is going to be a monitor class. Okay, Java doesn't know about the monitor class. Always know that the synchronized methods cannot be executed at the same time by two different threads. So let's look at this insert thread, and insert method. It will not have any code regarding my mutexes. Okay. Any questions? Let's see. Where are questions? Questions? No questions. Okay, good. I don't know why I cannot. Can I do this like that? And this. No, doesn't work. How can I just get rid of this part and meeting chat? These are my participants. I don't want to see the participants. I don't want to see this part. Somebody has their microphone on. It is making a noise. Let me see who is it. Gonna find it. Anyway, I will switch back and forth. I don't like it, but that's what I'm gonna do. Switch back and forth. So let's look at the implementation of the. Let's look at the implementation of the insert method. Insert method is a synchronized method. It takes an integer. It doesn't do any mutual exclusion. It says that if count is n, then that means that there is no buffer space available. So I will go to sleep. Go to sleep is a method, stupid method. It just says that wait. Okay. Just call wait. What kind of a method is this? Where is this wait defined? This is Java. This is an object-oriented programming system. So there are no global functions like C. Where does wait come from? Remember wait? You might say that wait could be, since this is a class monitor, it doesn't extend from anywhere. Like there's not a thread. You cannot say that it's an inherited method from thread, and this class is not an inherited class. So where does the wait come from? Answers. Where does the wait come from? Somebody's, yeah. Gökçe, I gave you already a praise. Just recycle that praise again. Object class. That's right. I mean, but Selman, the Selman's answer is better than Gökçe's answers, because object is a well, object class is object class, right? With not the capital letter. Java object class. Okay, Oracle. Yes, class object. So the O is capital O, and remember the object class. Clone equals finalize. These are the methods. Wait, okay. Wait, notify all, and it looks like there is a timeout wait. So I'm going to wait for this many. So what I am waiting with the wait, what am I waiting? I am waiting until somebody notifies me. So causes the current thread to wait until another thread invokes the notify or notify all. So that's what I do with the Java. It says that let's go to sleep. In a try catch block, calls wait. Okay, this wait will wait there. This wait will wait there until somebody notifies me. I mean, with the wait there could be some exceptions it's throwing out, so I need to catch them. Otherwise, I would get unhandled exception error, etc. So they don't want to write this code inside this part, so they made a simple function. So if count is n, then wait. If count is not n, that means that it has to be smaller than n. Then at the high index, I put my value. I increment high by 1 and take the modulo of n, increment the count by 1. If count is 1, that means that the buffer didn't have anything before. Now it has something. I am notifying whoever is sleeping with this monitor. Okay. And then remove does exactly the opposite. If count is 0, go to sleep. Otherwise, if the count is not 0, then I can take the low index part of the buffer out, increment low by 1, modulo n, and decrement count by 1. If count becomes n minus 1, then I need to notify any producers that are waiting to fill that part in. And at the end, I return the value. Okay, so as you see, I don't care much about the mutual exclusion. Condition variables are already there. I mean, condition variables are my count, my buffer, etc. I don't need to think about what happens. Is there a race condition on my count variable, low variable, high variable, or buffer variables, since they are globals? No, I don't have to, because I know that this is synchronized and this one is synchronized. Because this is a monitor, no two threads can be inside the insert or the remove method at the same time. Good. Okay, any questions? So Java does it this way. So as you see, there are many ways to achieve the same effect. I mean, I gave you maybe 4 different versions of the same producer-consumer example, using the semaphores, using the condition variables, etc. It could happen. But I mean, depending on the operating system, depending on the programming language that you use, there might be more convenient cases. There might be stuff that you need to be careful about, and you should know about these. This is an operating system course. We don't talk much about how to use these kind of structs for specific cases, but without knowing some kind of detail, I cannot tell you how these are implemented. Okay, good. So let's continue. So monitors are nice, but what are their disadvantages? The disadvantages are these. They are only available in very few languages, like Java. In C++, we don't have them. But if you like, you can implement something like a monitor. And there are some libraries that implement monitors in C++. Okay. Monitors, semaphores, mutexes, they are fine on single machine, even a multiprocessor machine. That's fine, but they fail if I like to communicate between 2 processes on 2 different systems. Okay, I have a computer, I have a PC, and I have another PC. There is a process and there is a process running in there, and they are connected using internet. How am I gonna make inter-process communication between these 2 processes? Okay, so in a distributed system connected via a LAN, local area network, whatever I told you up to now doesn't work at all. So what is the solution? Solution is message passing. Okay. Depending on the operating system, depending on the programming language that you use, it is possible to send and receive data to and from some other destinations on the net. Okay. You say that this is my destination. This is the message that I am sending. This is my source. This is the message that I like to receive. Okay. This is a buffer. Just fill this buffer in. Okay. The receiver blocks if there is no data available. If the data is not available, I am blocked. Sender blocks if the receiver's buffers are full. Okay. There are many things about the networks happening, like the acknowledgements, flow control, error detection, correction, message ordering, etc. I mean, these are important questions, but we are not going to talk about them because they are related to the networking. Okay, but of course, I will show you a simple program that uses sends and receives to do this producer-consumer problem. Okay, this is the example. Buffer is n. There are n available slots. Let's look at the consumer first. Consumer runs this. Consumer runs this code. It says that, okay, I have two integers, item and I, message m. At the beginning of the consumer's life, it directly sends n messages to the producer. It says that I have the address of the producer. I am going to send n empty messages to the producer. Okay, that's what it does at the beginning. So let's go back to the producer now. The producer says that, okay, I will produce an item first. I will get an empty message from the consumer, okay. I will put my item into this message and I will send it to the consumer. So the producer doesn't send the produced item directly. It needs a empty buffer first, then sends it to the consumer. Without receiving an empty buffer, it doesn't send anything. Okay, for the consumer, it says that, okay, I have sent n empty buffers. I need to receive a buffer now, and I extract item from that buffer. Okay, and I am sending another empty buffer to the producer, and I consume the buffer. Okay, so it looks kind of weird. Why did they implement it this way? Why did I need this part? Okay. Okay, if I remove that part, okay, I don't have to receive anything from the consumer. I just produce the item, build the message and send it, right? And this one, I don't need to send anything to the producer, right? I just receive it. So I receive, I extract it, and I consume it. I produce, I build the message, and I send it, right? So why did they choose it this way? Just produce and send, receive and consume, right? Why did they implement it this way? Kamil, you are asking a question about the monitors, and keep that question, and I will come to it later. You answer my question. Why did they implement this message passing case this way? Anybody has the answer? What do you mean, Doğancan, synchronization? Well, this whole chapter is about synchronization, yeah. Yeah, Mehmet, you have a point. Yeah, to learn the buffer size. I mean, otherwise it looks like if I just produce and send, that means that I have infinitely many buffer size. I mean, how am I gonna restrict it? How am I gonna say that I can send at most 100 buffers? Okay, this is a way. This is a way to just limit yourself in terms of buffers. If n is 10, that means that there could be at most 10 buffers available. I can send at the same time 10 buffers. Okay, that's how we solve that problem. Okay, so that was the idea. So if we go back to Kamil's question, what can go wrong when they try to sleep? Oh, you mean when we say wait? When we say wait in Java, we are catching an exception. Are you asking me what would be the case? I mean, these are complicated stuff. When you try to wait, sometimes it says that the Trez library is not ready, and etc. and etc. I don't know exactly, but okay, just a minute. Okay, just wait. Let's look at this one. throws illegal monitor state exception if the current thread is not the owner of the object's monitor. So it can throw an exception. If the current thread is not the owner of the object's monitor, then it will throw a, because it's a monitor, right? If it's a monitor, anybody can call. If the current thread is not the owner of the object's monitor, then you're gonna get an exception. Another one, interrupted exception. If any thread interrupted the current thread before or while the current thread was waiting for a modification, then you will get another interrupted. So these kind of stuff can happen. And some of them may not be possible for some operating systems. Some of them are possible. So the correct thing is that if a method can throw something, then you need to write a code that catches it. So as you see, we didn't do anything. I mean, the catch statement didn't do much. It was a stupid catch statement. Okay, good. So let's go back. So again, we need these. We need these lines. I cannot delete them. Okay, we need these lines so that we can restrict the number of messages in our buffer. Okay, good. Any questions so far? So we talked about inter-process communication so far. I mean, this chapter, chapter number 2 is a very long chapter. It talks about many things, and those are each part of this chapter number 2 is a complicated subsection. And in fact, this chapter 2 is how many pages? I think it's the longest page chapter of the book, 85 to, yeah, it's like 80 pages or 90 pages, 85 pages. Yeah, it's like a book, right? 85 pages of very dense information. So at the beginning, we talked about the processes and the parallelism, the states of the processes, etc. Then we talked about the process table, what we mean by process table. Then we said that processes are too heavy. Let's talk about threads. With the threads, we have the user level threads and the kernel level threads. We talk about the POSIX threads, how we implement them, right? And then after that we talked about inter-process communication. Now we will talk about scheduling. Okay, scheduling is a technique that has to be used with multiple threads and multiple processes. These are the questions regarding scheduling. We have several processes are runnable. I don't know why I have this question mark. The question is which one is going to be run next. Okay, how am I going to make this decision? Okay, A and B and C and D are all available. How am I going to make this decision? One decision could be just random. Choose a random one. That could be a scheduling technique. Okay, choose a random one. And sometimes behaving random is very efficient because the code for random scheduling is so fast, so you don't spend too much CPU time. And when you say it is random, it is fair too, right? I mean, you are not favoring anybody. It is fair. Everybody is treated the same. But sometimes randomness is not a good solution. For example, randomness cannot handle priorities. Randomness cannot talk about I/O intense or CPU intense jobs and etc. So we need to come up with better ideas, better than the random scheduling. Okay. So your schedule, the behavior of your scheduler will depend on your environment. What do I mean by this environment? Because if you are in an old batch system, okay, let's say you are in a second generation computer room, okay. How did the second generation computers work? Do you remember those? The second generation computers, there was a very large computer, okay, IBM 71 something, okay. Since this was a very expensive computer, I had a small IBM 1400 computer there and ITM another 1400 computer. So I loaded tapes. Tapes are loaded. This one writes to tape. And for this one, I have punch cards, right? I have punch cards. So this one writes to a printer. So this printer gives me my outputs back. So who puts these punch cards to this computer? An operator, right? Another operator takes these printers out. Okay. So the scheduler in those days is this operator. This operator makes a decision who runs first, who runs second, who runs third. Because this is a batch processing machine. It doesn't do multitasking. It doesn't do parallel programming. Whoever comes in with this tape, they will run first. Okay, that's a batch system. In fact, those batch systems are still working the same way. First come, first served. Okay. So during those days, the scheduler was the person who loaded the card decks onto the tape. After that, the third generation computers, when we had the multi-programming time-sharing systems, okay, then we started having issues. I mean, if first come, first served is the scheduling mechanism, then our time-sharing users will not be happy. Why? Because they say that I hit this enter button. I am waiting for 10 minutes. What's going on? You don't wanna make your users wait for that period of time. Then it's not a time sharing machine, right? So your priority should be given to time sharing requests or the interactive request. Maybe the batch jobs should wait. Okay, so I need to make these kind of decisions. I mean, during those days they invented this. Even still today, higher priorities are given to the interactive requests. Okay, backing up your data, doing some memory management or memory arrangement can wait. Interaction is more important. Interaction is more important. Okay, good. So the scheduling decision definitely depends on your environment, and we are going to look at the scheduling decisions by looking at the environments first. Are you on a batch environment or an interactive environment or a real-time environment? Those are the criteria that I need to check first before I make my scheduling decision. Okay, for that maybe I should look at the process behavior too. There are some processes like this. Okay, for a long CPU time, they do some calculation, then they take a break. They say that I need this from the desk. I need to send this data to the network. Then again, another long period of time that uses the CPU, short period of time for the I/O, long, and this is a CPU bound process. A is a CPU bound process. B doesn't behave that way. Okay, it's an I/O bound process. It just immediately needs user interaction, immediately needs some disk I/O, immediately needs some network input output maybe. So the short CPU burst, long CPU burst, these are the behaviors of the applications. I cannot say that this application is written better than this one because that's the nature of the application. Maybe this one is doing very intense scientific calculation. This one is a typical word processor, right? Word processors usually they don't use the CPU much. Okay, they just wait until you move your mouse or until you press one of the keyboard keys, right? So you cannot say that my process is behaving this way. It's a bad process. It's just the nature of the process. So my scheduler has to handle these kind of cases. And it looks like I need to give more priority to this kind of a process. Why? if I keep the priorities of these two the same, this one will use more CPU time than this one, right? This one will use, let's say, this is 100 seconds, okay? 0 seconds and 100 seconds. Out of 100 seconds, this one will use maybe 50 seconds of CPU time. This one will use maybe 10 seconds of CPU time. So at the end, I may say that, okay, this is not fair, okay? This is not fair. Maybe if this one needs a CPU, this one should have a higher priority so that this will use more CPU time. It's not this process's fault that it's a I/O bound process. Somebody has to write I/O bound processes, right? Okay, so we are going to look at this kind of process behavior too. Processes alternate CPUs with dia request. Okay. So CPU bound processes think more than they reader, right? And CPUs have been getting, since CPUs have been getting much faster relative to the disks, okay, these durations are getting shorter and shorter. So they are waiting for the disks a lot. Okay, so maybe, as I said before, if I have a I/O bound process, maybe I should increase their priorities. Maybe my scheduler should say that this one should work more often than the other one. Okay, so this kind of scheduling decision depends on the process behavior. Okay, any questions? I don't see any questions. Good. So when do I make this the scheduling decision? Of course, when I make a new process or a new thread, if I have a single CPU, if I make a new thread or new process, then I need to make a decision. Should I continue running the parent process, or should I start running the newly created child process? Okay, a scheduling decision. When a process is using the CPU and the process said that operating system, I am done, I am terminating myself, so I need to make a decision who's going to run next. When a process is blocked, the process made a system call and it is blocked, so somebody else has to use the CPU. When the I/O completes, when the interrupt says that this data is ready, then whoever is running is interrupted, and the operating system has to make a decision. Since the data is ready, if somebody is waiting on it, then I need to make a decision. Should the interrupted process continue, or the process that needed the data should continue, right? So that's another question. And sometimes after the timer interrupt, I got a timer interrupt, and if I think that current process took too much CPU time, maybe I can make a scheduling decision. So these are the points where I need to make a scheduling decision. A scheduling decision depends on the environment and the process behavior. Okay, so let's look at this concept of preemptive and non-preemptive schedulers. This is a very important concept. Very important concept. Okay. A non-preemptive scheduler, it will let a process run as long as it wants. Okay. That scheduler switches between the processes whenever that process is blocked. Okay. How does the process gets blocked? Okay, how does the process get blocked? It gets blocked whenever it needs data from the disk, whenever it needs to send some information to somewhere else, etc. So this non-preemptive scheduler doesn't interrupt a running process as long as that process likes to run. Okay, so all the computers, early version computers, first generation, second generation computers, or the early personal computers, they are using non-preemptive schedulers. Okay, when I get the CPU as a process, I use the CPU as long as I want. Okay. On the other hand, preemptive schedulers, they say that Okay, I will set up a timer maybe for 50 milliseconds. After 50 milliseconds, I will get an interrupt and I will see if the process is still continuing. If the time used by the process is more than a quantum time, then I will make a switch. So this is preemptive. Even though a process wants to continue, the operating system says that no, stop. You don't wanna continue. Okay, you're gonna stop. I will suspend you. I will block. I will put you at the ready queue, but you will not use the CPU. Okay. So preemptive is more complicated. I need a timer. That's a hardware component. I need a timer, and I need to handle the interrupts produced by that timer. Okay, that's the preemptive scheduling. Of course, if you don't have any clocks available, then you cannot do preemptive scheduling. All you can do is non-preemptive scheduling. Okay, so that's the difference. The current operating systems, the modern operating systems, almost all of them, they are preemptive. They have timer devices, and those timer devices cause interrupts, and operating system handles that interrupt, and it makes a decision to make a switch between the processes. Okay, any questions so far? No, nobody asked any questions. Okay, let me take one or two questions, then I will stop after this point because I am out of time. You have any questions? After this point, I will try to look at the environment. If our environment is a batch environment or interactive or real-time environment. I think the early versions of Windows, I think Windows 3. Windows 1. Okay, let me see. Windows 3.0 preemptive. Let me see if it is preemptive. Okay. Computer Windows 3 control. Where is that? Okay. This mode enables VDMs limited preemptive multitasking of VDMs and demand page virtual. However, it is protected mode was the same as 2. So it looks like Windows 3.0 is not preemptive. To make it preemptive and partially preemptive, you need the enhanced mode, because I think Windows 3.0 could run on earlier versions of Intel CPUs, and those were very limited in terms of supporting multiprogramming. So preemption, in terms of preemption, I don't have it. Okay, you just read it. You just read when Microsoft made the preemption available for the Windows environment. Okay, any questions? No questions? If there are no questions, what about Ihsan? What about time-dependent applications? Notify user at 12:30. Is it time quantum causes lapses on time? Well, I mean, if the time is critical for you, very, very critical time, I mean, you mean the calendar application, right? At 12:30, just notify me, right? Okay. Well, we are talking about the 50 milliseconds time for the quantums. I mean, if you are late 50 milliseconds or 100 milliseconds to notify your user at 12:30, then that's going to be fine. But if that time is very, very critical, if you are running in a real-time environment, then maybe you should not depend on that kind of a operating system feature. I mean, your whole operating system should be a real-time operating system. So most of the time we make the approximations with the times. We will talk about this when we talk about the I/O, when we talk about the timers in the I/O section, I/O chapter of the book. Does real-time OSs are non-preemptive? Kamil, that's a very good question. I am going to send you a praise, but I think I sent you already as praise, right? What was your praise? Did I send you a praise? No, you don't have a praise. Okay, I'll send you a praise. But okay, choose a random one. Team player. Okay. The answer is surprisingly no. Real-time OSs are not preemptive because they don't have to be. All the tasks are time conscious. When they run, they say that I will take at most 30 milliseconds. I will not take more than 30 milliseconds to complete the job. Okay. So everybody knows this. That's why real-time systems, writing applications for real-time systems has to be done very, very carefully. They are not general purpose computers. Okay. But the answer is yeah. I mean, you would expect that real-time operating systems are preemptive. No, they are not. I mean, if they are preemptive and they are relying on this feature, then they cannot be real-time operating systems. And we will talk about it on Monday next week. Is there any benefits to having a non-preemptive also? Of course. I mean, if you don't have the timer, right? I mean, you have anything, you have no other options. If you don't have a timer hardware, your timer doesn't produce an interrupt, then you cannot have a preemptive operating system, or you like to keep your operating system very, very small. You don't want to deal with handling timer interrupts. That's a complicated thing. So what you do whenever timer interrupt happens, you don't do much. You don't do some bookkeeping, and you just return. Okay. So having a non-preemptive operating system means that you have a simple operating system, which would be useful on embedded systems, right? Very, very light systems, or very, very light operating systems. Okay, Mohammed, I will give you a praise for that one. Okay, problem. So kind heart. There are so many Mohammeds. Okay, good. So I'm out of my praises today. Sorry. I will give you more praises next time. Okay, that's it for today. We will continue on Monday. By the way, your new homework, it is all about preemption. It is all about scheduling. It is all about making decisions between the processes. Okay, so be careful about that homework. Try to do it as good as possible. Okay, thank you. So I need to find a way to, how do I